First, these two expressions, a square omega plus ab omega square plus ab omega plus b square omega square. A square omega, ab omega square, ab omega plus b square omega square. I am using here modulus amplitude or polar form. Z1 equal to R1 cos theta 1 plus I sin theta 1 and Z2 equal to R2 cos theta 2 plus I sin theta 2. Then different types of problems. If omega be a complex cube root of a unity and values of x, y, z are these, then we have to prove this. X square plus y square plus z square is to be shown as 6ab. I start from the left. Put the values. Plus a omega square plus b omega whole square. Use the identities. A square plus b square plus 2ab. A square omega square plus b square omega to the power 4 plus 2. Product of these two means ab omega cube plus a square omega to the power 4 plus b square omega square plus 2 ab omega cube. We have used the identities for a plus b whole square. Then I first consider a square terms. A square within brackets 1 plus for this omega square omega to the power 4, that is equal to omega cube plus 1. We mention here plus omega, then b square terms, b square 1 plus. I like to use these symbols. Similar terms have been marked by the same symbol. Then this is omega to the power 4 means omega plus omega square. Then 2ab terms. 2ab from this 1, from this omega cube, from this one also omega cube, therefore this is equal to a square into 0 plus b square into 0 plus 2ab. 1 omega cube is also 1, that is 1 plus 1 plus 1, that is equal to 6ab. RHS proof. You follow? In the first step, what we have done? used the identity for a plus b whole square, then since we have to show 6ab, that means a square terms and b square terms will vanish. For that, keeping that fact in mind, I have first taken a square terms together, then b square terms together, then 2ab terms together. And after simplification, we get the result 6ab, that is the RHS part. Now, the second one, LHS, X, Y, Z. First I put the values A plus B, A omega plus B omega square into A omega square plus B omega. I shall multiply successively. First, these two expressions, A square omega plus AB omega square plus AB omega plus B square omega square. A square omega, AB omega square, AB omega plus B square omega square. Then A square into A omega square plus B omega. Now A square omega plus AB omega plus omega square plus B square omega square. The whole is to be multiplied with A omega square plus B omega. Again I apply distributive law of multiplication. Then I multiply the whole by this term first, then A cube omega cube. I have taken first this one plus A square B within brackets omega cube plus omega to the power 4 plus A B square omega to the power 4. After taking the product, you first check whether you have written correctly. A omega square into this omega cube, A cube omega cube, then A square B within brackets I have multiplied omega square, omega cube plus omega to the power 4, then this into this A B square omega to the power 4 plus A square B omega square B omega into whole plus A B square within brackets omega cube plus omega square plus omega cube plus B cube omega cube. Now I shall apply those two relations, omega cube equal to 1 plus omega square equal to 0. Then this will be A cube. This 1 will give omega cube, this 1 finally A cube. Then the last one will be B cube plus A square B terms, that means these two terms. Omega cube means 1 plus omega to the power 4 means omega, and from it will be omega square, then AB square term. From this omega to the power 4 means omega plus omega cube is 1 omega square. That means a cube plus b cube plus a square b into 0 plus ab square into 0. Finally, a cube plus b cube RHS proved. Now I am going to discuss properties related to modulus, amplitude and complex conjugate of given complex number or numbers. First of all, properties related to modulus amplitude. I will discuss serially. Number 1, modulus of Z1 plus Z2 is less than equal to modulus Z1 plus modulus Z2. Also, this will hold for the difference of the two complex numbers. Then, number 2, modulus Z1 minus Z2, which will be greater than equal to that means modulus of Z1 minus Z2 is greater than equal to modulus of the difference of modulus Z1 and modulus Z2. First, let me discuss the proof of the first one. The others, I suggest the students, those who are interested, you can solve yourself or see from your textbooks. Proof for the first one. I am using here modulus amplitude or polar form. Z1 equal to R1 cos theta 1 plus I sin theta 1 and Z2 equal to R2 cos theta 2 plus I sin theta 2, where R1, R2 are moduli modulus, I use that, of Z1 and Z2 respectively. And theta 1, theta 2 are amplitudes of Z1 and Z2 respectively. Therefore, we can find easily Z1 plus Z2, that will be equal to, first we count real part, that means r1 cos theta 1 plus r2 cos theta 2 plus I r1 sin theta 1 r2 sin theta 2. Therefore, modulus will be equal to, if a plus ib be the complex number, then modulus will be under square root symbol a square plus b square. That means now if I square both the expressions, then I take r1 square term together, then r2 term together, so that r1 square cos square theta 1 plus r1 square sin square theta 1, then taking r1 square common factor, that will be equal to r1 square within brackets cos square theta 1 plus sin square theta 1, that is 1. That is why I have written directly r1 square plus r2 square cos square theta 2 r2 square sin square theta 2, taking r2 square common factor, then within brackets there will be cos square theta 2 plus sin square theta 2 means 1, finally r2 square, then plus 2 r1 r2 term. From this expression we shall get cos theta 1 cos theta 2. I write that. From this one we shall get 2 r1 r2 sin theta 1 sin theta 2. I have taken 2 r1 r2 common, therefore it will be that means finally r1 square plus r2 square plus 2 r1 r2. Now this is cos alpha cos beta plus sin alpha sin beta form, that means cos of alpha minus beta. There it will be cos of theta 1 difference theta 2. Now value of cos of theta 1 minus theta 2. Less than equal to 1, or we can say minus 1 less than equal to cos of theta 1 minus theta 2 less than equal to 1. That means this 1 will be less than equal to therefore I can say modulus of z1 plus z2 is less than equal to r1 plus r2, and r1 is already I have mentioned, therefore mod of mod of z1 plus z2 is less than equal to mod of z1 plus mod of z2. Therefore, we have proved the first property. Taking minus also, we can show it will be r1 minus r2 whole square, that is of course less than equal to r1 plus r2 whole square. From that, final conclusion is this. Therefore, the first inequality relation is proved. Now, the second one can be proved easily. For the second one, mod of z1 can be written as, within modulus symbol, sum of modulus of z1 minus z2 plus z2. Now, if I use this property, it will be less than equal to students will note. Now, we transfer this one on the left. Therefore, modulus of z1 minus z2, that will be greater than equal to mod of z1 minus mod of z2. I call this relation as A. Then we can write modulus of z2 is equal to using the similar concept we can write therefore if we combine now these two, we get modulus of z1 minus z2 combining A and B. You see, this is difference of moduli of z1, z2, and this is difference of moduli of z2 and z1. Therefore, combining we can write modulus of z1 minus modulus of z2 whole modulus. Therefore, the second one is proved. Now, product quotient related properties. I mentioned like this. Number 3, modulus of z1 into z2. That is modulus of product of two complex numbers. That will be equal to product of the moduli of two complex numbers. You can prove easily, very easy. Also, you can prove by taking Z1 equal to say A1 plus B1I, Z2 equal to A2 plus I B2, then get the product and find the modulus and also calculate the right hand side. You can prove easily. I am not proving. I suggest students you prove yourself. Very easy proof. Number 4. In case of quotient, that means modulus of quotient of two complex numbers is equal to the quotient of the modulus of those two complex numbers. Also, generalized form for this one is applicable. That means modulus of Z1 into Z2 into Z3 Zn, that will be equal to modulus of Z1 into modulus of Z2 into modulus of Z3, etc. I am saying this one. Sorry, Zn. And in case of quotient, remember one thing, modulus of Z2, that is not 0. Therefore, these are the properties related to modulus. In the next episode, I shall discuss about the argument of product and quotient. Thank you.